I'm Andrew Jackson. I am from the University of Edinburgh, and today I'm going to be talking about the verification of analog simulations. So just as a quick note, this is going over a fair few different projects. So some of this will have been work done at Warwick with Animesh and Theo, and as part of the QuEVEC program from a few years ago now. Okay, so just getting started. It's maybe worth to talk about a little bit, because I'm not doing annealing, which I think a lot of people have a background in annealing here. Hello. It might be worth talking a little bit about why we might actually want to be analog when we're simulating in the first place. So the basic answer to that is you can actually get much, much larger simulations with much, much lower errors than you can if you were to do something like a digital simulation, which is like sort of, trotterizing and then implementing each thing in some sort of gate system. So there's an example here which is quite useful that just sort of shows that, yeah, analog simulators are already far ahead of what a digital computer can do. Okay, so it's maybe worth to quick mention exactly what kind of verification protocol we're going to be doing. And so for those uninitiated, a verification protocol is essentially a way of establishing some confidence in the computation that you're doing. So what we're doing here is we're literally just taking a bunch of computations. Some of them are going to be the computation we want to do. Some of them are going to be specific, what we're calling trap computations. And the aim of them is just to somehow experience the noise in the same way that the target does and use it to make some sort of deductions about the system. Okay, so the first one to talk about is the original analog quantitation protocol. So this was the first method to verify the outputs of analog simulations. Before that, the non-universality of analog devices caused a fair amount of difficulty in actually building these trap models. And essentially, what this now gives is a bound on the total variation distance between the ideal case, as in there's no noise afflicting your system, and what you actually get out of your system. Because we live in the real world, and hence a system is actually going to interact with the environment. It's going to have all sorts of issues with it. Okay, so what we actually require from an analog simulator to be able to do this is the ability to implement, well, in our case, we're using the XY interaction, which has the kind of Hamiltonian that we've shown there. This has the useful property that it's universal, which is a kind of technical term, but it essentially means I can emulate any kind of Hamiltonian that I'd like to by encoding the state that goes into this. The downside of this is that I actually now need 2-qubit and single-qubit gates in my in my simulator to be able to perform this. Okay, so just to quickly go through it, as you can see here, these V gates and this V inverse gate are what we use to do the encoding and the decoding. These time evolutions here are each according to the Hamiltonian that I've shown in what I'm calling equation 1 here. And we'll talk about a few of these other bits here. But the main point to focus on, really for our purposes here, is the V gate, the V inverse gate, and everything between it, because that's kind of what's going to be the technical bits that we are going to focus on. Okay, so first it's going to be quick talking about what is time inversion, because this is going to end up being at the core of our trap circuits. And for us, all time inversion is it's a sub-circuit that implements a true time evolution. And then we need some method of adding only single-qubit gates to this sub-circuit so that the time evolution now goes in the opposite direction. So what we can sort of see here is that if we set all these C1, C1, C2, C3, all those things down there, if we set them to the identity, you can see that this little block in the middle here of just the time evolutions would just do the time evolution for duration t. However, if we were somehow able to find some T-gates, if we were to find some single-qubit gates, such that this second time evolution can be inverted, as in made to go in the opposite direction, then what it will do is it will cancel out with this first time evolution. The whole thing collapses down to just the identity, and hopefully you can see then this V and V inverse gate would cancel, and then hopefully you can see all these single-qubit gates here would then also cancel. And this has the result of giving us our trap. So now we know that in the ideal case, our trap should reduce the identity. We put all 0 states in, we measure in the Z basis. So what we should do is we should be able to then measure the identity. Okay, so, sorry. It's maybe quickly talking about how time inversion works. So the basic trick is this lemma here. And what this lets us do is it basically means that if I put two gates around a time evolution, its inverse, what it lets me do is I can then move it up into the exponential. So when I'm considering how I'm going to invert a time evolution, what I can actually do is I can consider instead just how can I invert the Hamiltonian itself. So what gates can I put around the Hamiltonian so I get a factor of -1 in front of the Hamiltonian instead. So again, this is sort of fairly standard stuff, but just so people see how this works, you just take the Taylor expansion, you can move them inside the summation, and then you can basically undo your Taylor series, and that gives you exactly what you need. Okay, so just to give an example that's going to be illustrated to how this works. So I'm going to take the XY interaction on just 2 qubits for now. And what that's going to be is a nice little toy example that shows how this works. So the basic theorem here is that if I apply a Z gate to just the first qubit, that should give me the inversion that I need, that I was talking about earlier. So you can sort of see how this works here. If I put a Z gate on either side of the Hamiltonian, because Z anti-commutes with both X and Y, these are both Pauli gates, by the way, we can sort of see that the overall effect is going to be that we're going to add a factor of -1 to the Hamiltonian. And then using the previous lemma, what this lets us do is it then lets us, effectively, we've reversed the entire time evolution here. So the generalization of this is that if I apply a Z Pauli gate to a 2 coloring of a graph that sort of represents the interactions, where each edge is an XY interaction, what I will have done is, regardless of the structure or the size of the system, I've now inverted the entire time evolution. And this is useful for exactly the reason, that I mentioned earlier and was in the diagram I gave, because now we can get the entire traps to collapse and at the same time experience the same error as the target simulation. This factor of them experiencing the same error is guaranteed by this, the assumptions that we have to make for this sort of system. So the basic assumptions are, some are fairly standard, so we're just saying the error is modeled by CP-TP maps, replacing what we actually intend to operate. That's fairly standard. It is a very general class of error maps. We do have to assume that if you run the same simulation multiple times, you're going to have the exact same TP-TP map, which is maybe slightly unphysical, but we needed that to begin with. And we need the single qubit gates to have error that's independent of the actual gate that it is. So it can depend on where and when in a circuit it is, but the error map itself can't depend on if you've got an X gate, a Y gate, a Z gate, whatever the factors may be. Okay, so just sort of moving on a bit, we have since upgraded this original protocol. So what we've really done to essentially make this whole situation a little better is, first of all, we found a way of inverting Hamiltonians so that we don't need to assume that we're using universal Hamiltonian. So we can say goodbye to this XY interaction that we like so much. And we can instead just use a general Hamiltonian. That makes life a hell of a lot easier, because now we don't need the extra qubits that we could potentially have, because mapping to a universal Hamiltonian can actually sometimes scale your system up by a polynomial factor. We now can also completely get rid of the 2 qubit gates. And what that means for us is that we actually have a much more physical system now, because if you go look at the hardware that's available for analog simulators, they are starting to add single qubit gates, or they're already saying they are in the near term going to be adding single qubit gates, but 2 qubit gates is a much less common proposition for them, at least. The cost of all this is that this new approximation scheme that I will talk about in a little bit is now approximate. We're not exactly inverting the time evolution. All we now do is approximately to arbitrarily good error. But we do have to approximate the time evolution being inverted. And also, we are now going to need a number of single qubit gates that depends on the the error to which you want to do this approximation to. Okay, so there's just a note. There's the paper that, this is quite an old photo, but still, there's the paper if you want to look that up of what this is. Okay, so, oh, hello. That's not me, there we go. I'm going to keep going, and hopefully this will behave. Okay, so the core change is that we now have a new method inverting Hamiltonians that I mentioned before. And this means that we, essentially the same stuff I said before, this means that we don't need universal Hamiltonians, and we also don't need 2-qubit gates. And we don't need ancilla qubits, again, the cost being that time evolution being inverted is now approximate. Okay, so just a quick way to talk people through what this inversion is going to be. This, just to be clear, is repeated m times, and we index loops by k. So these B gates are going to change in each loop. And what you can hopefully see is that if I was to set all of these B gates to be the identity, this would perfectly implement the time evolution forward. But what we're hoping to be able to say is that if we're going to hopefully find some values of these B values that would let us effectively approximately invert the time evolution, then this would be a perfectly functional time inversion itself. Okay, so just to be clear, based on the last protocol that I showed you, the way you'd upgrade to this new one is you'd take out all of the things between, including the V and the V inverse gates, pop them all out, and you would just replace it with this whole thing here. So hopefully you can see this is much less, well, you can sort of see the cost is we need to break the time evolution up into more small time evolutions. This is so that we can put these single qubit gates in between that do the inverting. But all that really means for us is that these are the single qubit gates that I mentioned before, so we need more single qubit gates. The total duration of the time evolution that you'll need stays exactly the same, so we're not adding that much depth to the circuit, we're just adding more single qubit gates. Okay, so it's maybe quick to just sort of say exactly what these B values are. So what you actually end up needing to do, and this is maybe a bit more technical than I'd state it in the easiest case, is you have to look at the Hamiltonian you want to invert, because now I said we can do this for any Hamiltonian, so we can't assume a particular form of the Hamiltonian, though we are assuming it's a linear combination of unitaries as a Hamiltonian. What you need to do is you construct this GH set, and what that really means is you take each term in the Hamiltonian and you make sure you have at least one term in this set that anticommutes with it. And then we need to slightly modify it because we can, again, so if you were to use the G gates as this G dash gate, that would be perfectly fine. But you can simplify it slightly by just saying we can lose a large chunk of this GH gate, just providing that we always have something proportional to every element in the GH gate in this G dash gate. And then what we get is if we choose these B gates uniformly from G dash, so again, G dash will be some set of Pauli strings, that hopefully is going to approximately invert our Hamiltonian as required. So you can sort of see a quick example of this. The first example is to literally just go back to the old protocol for inverting time evolutions. And you can sort of see that because G inverts with, because a Z anticommutes with both X and Y gates, if we just have our G dash being Z1, this works perfectly fine with the new protocol, so we, in fact, recover the old protocol. You deterministically choose the one element you have from your random set. A slightly more complex case is if we wanted to add an extra term to this system, we would then have to add an extra term to this G dash H gate set. This is just to account for the fact that the Z itself doesn't commute with Pauli Zs, and so we need to add a new term that, what I'm saying, the Z gate does commute with, obviously, Z gates, so I need to add another gate in this case and it could be a Y, it could be whatever, it doesn't really matter, providing it anti-commutes with Z gates, and then that will give us a perfectly valid G dash gate that works out. So There's another slight modification which basically just says once you have your first G prime gate set, remove the identity for it. That makes life a little bit simpler. And so, as before, the way this works boils down to basically just taking Taylor series again. So if we take the time evolution and we break it up into lots of smaller and we break it down, what we can see is that to first order, if we have random choices from this G double prime gate, this will cancel out to have no error, and it'll be the same. But what you will see is that we keep these higher order terms, and this non-exact sort of cancellation and these higher order terms remaining is exactly what gives us the approximate nature of these time inversions. So again, you can hopefully see that this term here will just cancel out, that will go to 0. And what we're looking at, sorry, by the way, is just the difference between the two methods. Okay, so the addition of the random gate is what actually is remove the cross terms from the above equation. Again, it's a bit technical, but you can see my recent paper, and I've got the arXiv note there. Okay, so the key point about the new inversion is that it, again, adds the single qubit gates to an implementation of the time evolution to transform it. The required value of m, which is the number of time steps you need to break the time evolution into, scales quadratically in the time of your time evolution and inverse proportionally to the maximum tolerable diamond norm error in the inversion. And okay, so it's really maybe worth talking about it's maybe worth talking about what this enables us to do. So what are the assumptions of this new analog accreditation protocol? So once again, error is modeled by CP-TP maps. I don't particularly see this as a cause for concern. I think that's quite a reasonable assumption in the first place. We now say that we can actually relax this. I haven't talked about this, but we say that simulations with more single qubit gates have performed worse than otherwise identical simulations. So again, this is what relaxes the assumption that identical circuits repeated twice have the identical CP-TP maps. All I'm really saying is, and this isn't really a theoretical sort of point, it's more experimentally derived. All I'm really saying is that if I add more single qubit gates to a circuit in places where there otherwise was just the identity, nothing's there, I can only really make the simulation worse. This isn't universally true. Like you can contrive little examples that look a bit like error correction that contradict this, but if you're going to do something fairly natural, this is highly likely to be true. And then we have another slight improvement where we say that we're going to have a weakly gate independent single qubit error, essentially meaning that we can now also allow a tiny bit of gate dependence into the error in the single qubit gates. But again, that's not really the end of the world for us, because again, single qubit gates, part of the reason why we can assume they're independent of their error is because they are so good. And if also, again, they tend to be the best aspect in any platform you really want to try and do quantum computing on. Because they all have such little error, the difference between them is very small in itself, sort of proportional to the actual size of the error. And that is all I've got. Okay, right, thank you.
All right, thank you, Andrew. Other questions from the audience? There's one over there.
Yes. First, thank you for the talk. I would like to ask, do you know about Jennifer's universal quantum computation and simulations using an entangling Hamiltonian and local unitaries paper? Do you know that paper? Because later on, like a lot of years later, they developed what is called now digital analog quantum simulation. I don't know if you know about it, but there's already a design protocol to, from any entangling Hamiltonian to the Hamiltonian, get another entangling Hamiltonian by using local unitaries. And one of the things that you can do with this protocol is switching the sign, which is this time inversion. I don't know if you knew about it.
Honestly, off the top of my head, I can't remember the title. I did get basically the trick that lets me roughly do the time inversions from the paper, but I can't off the top of my head remember if it was exactly that one. So I honestly, I don't know. But the paper I did get it from did have an idea about you can map general Hamiltonians to other Hamiltonians.
Yeah.
So actually, it sounds like a decent plan. That was the one. It's in the paper. It's cited. So if you wanted to go check that, it'd be there.
Okay, thank you.
Yeah. I think you can use this one.
Yeah, so I think I saw a slide where you showed us that the first order cancels. Yeah, this one. So it means that your results are correct up to first order errors of time, right? So if you, let's say you want to go to t cube by m cube or something, then can you do that? Or by using more complicated, let's say, not just one local, maybe two local terms or something?
Okay, so I don't particularly know how you would do it, but I can't categorically say that there's no fancier way of doing it. I imagine it would be a fair bit more sophisticated than the way we're doing it, and I don't know if, do you know if there's a way of doing it?
Yes.
Okay, there's a way of doing it.
Okay, that's great.
Actually, was your hand raised to comment on this? Okay. Yeah, okay, actually, I also had a question, but maybe it's actually related to this issue. Maybe if you can invert signs, the question would be like, can you use this to turn like a stochastic Hamiltonian to a non-stochastic one for like simulations, right? When it's like a... Sorry? To turn like a stochastic Hamiltonian into a non-stochastic one, which relates to what Pauli was talking about with like the sign of the XX term, right? If you can flip that.
So to my mind, I like... So what you can actually invert using single-qubit gates is in some ways quite restricted in terms of what you can invert exactly. If you were trying to invert specific terms within a Hamiltonian, that may be a bit more tricky, and you might need to be a bit more lucky and a bit more, you might take a bit more thought in how to invert just single terms. But what you'd basically need is single-qubit gates that would invert just that term.
True. Yeah.
And not the other ones. If you were happy to do it approximately, then it might be a bit easier with the sort of methods we've got here. But I've not really considered that too much because I'm not really in the annealing.
Fair enough.
So I don't really...
All right. Okay, then thank you very much, Andrew, again. And the next speaker